Certainly. Here's a concise explanation of columns based on their structural use. Columns based on structural use. In structural engineering, columns are vertical structural elements designed primarily to support compressive loads. They transfer the load from beams or slabs above to the foundation below. Based on their structural function and use, columns can be classified into several types. 1. Load-bearing columns. Purpose: carry and transfer vertical loads from slabs or beams to foundations. Application: common in framed structures such as residential, commercial, and industrial buildings. Characteristics: designed for axial compression and sometimes bending moments depending on load eccentricity. 2. Non-load-bearing columns, decorative or architectural columns. Purpose: serve aesthetic or architectural purposes, not intended to carry structural loads. Application: found in facades, entrance porches, or interiors for visual appeal. Characteristics: may be hollow or solid and made from materials like stone, wood, or fiber-reinforced plastic. 3. Short columns. Definition: columns with a height to least lateral dimension ratio less than 12. Behavior: tend to fail by crushing rather than buckling. Structural use: suitable for structures with relatively low slenderness where compressive strength governs. 4. Long, slender columns. Definition: columns with a height to least lateral dimension ratio greater than 12. Behavior: more likely to fail by buckling rather than crushing. Structural use: common in multi-story buildings or where architectural height is needed. 5. Axially loaded columns. Purpose: columns that receive loads applied along the central axis. Use: ideal in symmetrical load conditions, common in regular building layouts. Design focus: simplified analysis since eccentric moments are negligible. 6. Eccentrically loaded columns. Purpose: designed to handle loads that do not act through the centroid of the section. Use: in buildings with irregular layouts or lateral load-resisting systems. Design focus: must account for bending moments and lateral stability. 7. Composite columns. Construction: made of a combination of materials, e.g., steel core encased in concrete. Use: utilized in high-rise buildings and bridges for combined material benefits. Advantage: offers improved fire resistance, load-carrying capacity, and ductility. Summary table. Column type: main use failure mode notes. Load-bearing structural support crushing/buckling primary load transfer elements. Non-load-bearing architectural not structural aesthetic use only. Short column low-rise/massive structures crushing stable and strong. Long, slender column tall/slim structures buckling needs lateral bracing. Axially loaded uniform loading conditions crushing/buckling easier design analysis. Eccentrically loaded irregular load paths bending plus buckling requires moment resistance. Composite high-rise bridges varies combines material strengths. Columns based on construction method. Columns are critical structural elements that transfer loads from the upper parts of a structure to the foundation. The method by which a column is constructed can significantly impact its strength, durability, cost, and suitability for specific projects. Based on construction methods, columns can be broadly categorized into the following types. 1. Cast-in-place concrete columns. These are constructed by pouring concrete into formwork on the site, around a cage of reinforcement bars. Advantages: seamless integration with the rest of the structure. More flexibility in shape and size. Suitable for complex or customized designs. Applications: common in residential, commercial, and infrastructure projects where on-site casting is feasible. 2. Precast concrete columns. These columns are manufactured in a factory or controlled environment and then transported to the site for installation. Advantages: high quality control. Faster installation on site. Reduced labor costs and construction time. Limitations. Requires careful planning and transportation. Jointing with other structural elements can be complex. Applications. Widely used in modular buildings, parking structures, and large commercial projects. 3. Steel columns, fabricated columns. Constructed from rolled or built-up steel sections, these columns are fabricated in workshops and erected on-site. Advantages. High strength-to-weight ratio. Rapid construction and ease of modification. Prefabrication allows precise dimensions and reduced on-site work. Applications. Skyscrapers, industrial buildings, and bridges. 4. Composite columns. Made using a combination of materials, typically steel and concrete. For example, a steel section encased in concrete or a concrete column with steel reinforcement. Advantages. Combines the compressive strength of concrete with the tensile strength of steel. Enhanced fire resistance and durability. Applications. High-rise buildings and structures requiring high load-bearing capacity. 5. Masonry columns. Constructed using bricks, stones, or concrete blocks, sometimes reinforced for added strength. Advantages. Cost-effective and easy to construct. Good fire resistance and aesthetic appeal. Limitations. Lower strength compared to concrete or steel. Larger cross-sectional area needed for same load-bearing capacity. Applications. Load-bearing walls in low-rise buildings and heritage structures. Each construction method has its own strengths and limitations. The selection depends on project requirements, load conditions, site constraints, construction speed, and budget. A sound understanding of these methods helps in choosing the most appropriate column type for a given structure. Certainly. Here's a concise and informative explanation about columns based on their load-carrying capacity. Classification of columns based on load-carrying capacity. Columns are vertical structural elements primarily subjected to axial compressive loads. Their load-carrying capacity is a critical factor in design and depends on several parameters such as material properties, cross-sectional dimensions, slenderness ratio, and end conditions. Based on how much load a column can carry before failure, columns can be classified into the following types. 1. Short columns. Definition: a column is considered short if its effective length to least lateral dimension ratio is less than a specified limit, commonly 12. Failure mode: fails primarily by crushing of the material due to direct compression. Load carrying capacity: higher load capacity compared to slender columns, as they are less likely to buckle. Design equation: equals P equals AF C, where P equals axial load, A equals cross-sectional area, F C equals compressive strength of the material. 2. Long, slender columns. Definition: columns with a high slenderness ratio, effective length is large compared to cross-sectional dimensions. Failure mode: fails primarily by buckling before the material yields. Load carrying capacity: lower than that of short columns due to instability. Design equation: Euler's formula equals pi 2 P CR equals KL 2 pi 2 EI, where P CR equals critical load, E equals modulus of elasticity, I equals least moment of inertia, L equals unsupported length, K equals effective length factor. 3. Intermediate columns. Definition: columns that fall between short and long columns in terms of slenderness. Failure mode: fails due to a combination of crushing and buckling. Load carrying capacity: requires empirical or semi-empirical formulas such as Rankine-Gordon or ACI formulas to determine. 4. Axially loaded versus eccentrically loaded columns. Axially loaded columns, load passes through the centroid, leading to uniform compression. They have maximum load capacity. Eccentrically loaded columns, load is offset from the centroid, causing bending in addition to compression, reducing load carrying capacity. Factors affecting load carrying capacity. Material properties, e.g., concrete strength, steel yield stress. Cross-sectional shape and size. Length and slenderness ratio. End conditions, fixed, hinged, free. Type of loading, axial, eccentric, lateral.